Alright, it's recording. Exercise 13E. Let's think. I've taught you how to solve exponential equations through what we called solving by inspection. But now we're going to move into actual inverse operations so that you've got an actual layout and technique. And how do you solve exponential equations? Just the same way as you did with linear. So x plus 3 equals 8. Just like you did with another linear, x times 3 equals 12. This time we've got now exponential base 3 to the power of x equals 9. So in each step, this one, remember I said the confusing part of logs and exponential is just the symbol. Yeah, so this one has a symbol for the operation. We say opposite of plus is minus. How much did I add? I add 3. So the opposite of that is minus 3. Whatever you do to one side, you do to the other. The inverse plus 3 minus 3 ends up being 0. They inverse each other because we want x to plus something to actually not change the value of x. X plus 0 does not change the value of x. That's why x equals 2. 5. That's what we want. Yeah, we want everything to undo so that we can get x by itself. Same thing over here. Opposite of times is division, so that's the symbol. The quantity is I times by 3, well then I divide by 3, and we know that the inverse times 3 divided by 3 is like saying taking 3 divided by 3, which is 1. X times 1 does not change the value of x. That is why we then say 12 divided by 3 gives you 4. So far, the pattern is, it's not the value, it's not the 0, it's not the 1. It's the fact that we haven't changed x. X stays the same. Okay? So it's what inverse operation allows for the x to stay the same. So when we do now 3 to the power of x, the inverse of base 3 is this symbol. That's your symbol. Okay? That log is the symbol just like you did with minus and division. The inverse of an exponential is log. Okay? Log is the operation. So I do log on both sides. The difference is though, what is the quantity? Well, the exponential was base 3. So the quantity is log base 3. Whatever you do to one side, you do to the other. So you can see I'm keeping it all the same. Whatever you do to one side, you do to the other. And we know that log base 3 of exponential base 3, they're inverses of each other. And that gives you x left over is equal to log base 3 of 9. So, what does that mean? That means there must be an operation that undoes all the base to solve for the power. Unlike previous operations, the inverse operation of exponentials is the symbol log. Okay, so I did the example just now. So here, if it's clearer, I'll just do it again. Log of base 3, log of base 3. So what I'm really saying is I want this. That cancels out. That's how you get log base 3 of 9. Okay, so it's whatever you do to one side, you do to the other. That helps you understand. So if I just rub that out to make it look cleaner, that's what you started off with. I did log base 3 on both sides. And we know that log 3 of 3x. And I can show you that on a calculator so you can see how it works. So you get familiar with it, yeah? So here, I'm going to use a calculator to illustrate a point. So say I take the number, I do x. X plus 3, take away 3. Still x. X times 3 divided by 3, still x. If I do now log, or 3 to the power of x, right? And then I do log. Now log is control. And if you look at the 10 to the power of x, there's an log there. Base 3 of, I need to move this inside. Let me do it again. So 3 to the power of x. See that? Is the inverse. These two are inverses, so what I should end up with is x as well. So these two cancel out. But the reverse also happens. If you can do x plus 3 minus 3, you can also do x minus 3 plus 3. So you can minus first, then add, and it'd still be the same. So if I did x minus 3 plus 3, so then that means for exponentials logs, you can also swap it around. You can also do 3 to the power of log base 3 of x. Because these two are the operations. They will cancel out based on the, again, quantity. Just like you did here, I just swapped it around. The answer should still be x. Starting to get what I'm saying? So the operation is the log, and exponentials just doesn't have an operation. It's just the positioning. So if you understand it that way, the way you do it for addition, subtraction, multiplication, division is exactly the same as what you would do for exponents. Logarithms. So in the past, there was actually a logbook. If you went to the info note, there was I saw one yesterday from 1890s or something. And essentially, it was a measurement. It has this measurement of a curve, which is the opposite of exponential. So essentially, they done one curve, and then they did the measurements for one curve. That's the inverse of the value. Okay, inverse just means that if it was 1, 2, then the other one would be 2, 1. Right? So they've done one for logs and had a log graph for it. So you, instead of what you're doing now, you can type it in a calculator. What they used to have is a table. You actually have to go look for decimal by decimal by decimal to know what it's like. It's kind of like your times tables. You have a times tables chart, okay, and there's 12 by 12, but imagine there was a times tables chart for infinite numbers that way, infinite numbers this way, then there was a log chart for you. If you want to do log 3 of whatever it is, you have to go look for the base, for the decimal, and then you're able to then calculate it. Now it's all done in a calculator. And the function's meant to be the opposite direction of an exponential. So the exponential goes up, logarithm's like the other way. So kind of like, I'll show you a picture later so that you guys can visualize. All right, team. So today is all about the algebra to work with logarithms. So here we go. In general, students don't do what I just showed them there. I want you to understand the algebra to it. Most students learn it this way. So a lot of teachers often tell them, say, a to the power of something equals y, and then you do this like rotation thing where you say it's log a becomes log a of y, and essentially you rotate the x over here and the y goes over here, and a goes down. Most students memorize that. I don't. I actually just follow that. Again, I follow this concept. Whatever you do to one side, you do to the other. That's how I come to this point. Okay? But if it helps you, you can memorize that, and essentially this is what they get you to practice to do. They'll say things like, if I gave you 3 to the power of 4, actually I'll make a different number. Let's do 5 to the power of a is equal to 99, right? According to this, then the log version of it is log base 5 of 99 equals a. So you can either memorize it that way. I like to read it. I actually read what the question's asking. Remember logs. What's log used for? Log is to find the power. Okay, so what it's asking is, it's saying, if I know I've got an exponential base 5, so log base 5, so 5 to the power of what gives me 99. That's why you're typing in your calculator. When you say log 599, you're asking what power, because whatever the answer is, what power for the base 5 will give the answer 99. That's what it's asking. That's why there's log rules. For example, when I give it to my year 12s and 11s, and they tend to try to memorize and they forget what it is. If I gave you this, and I said, what does that equal to? Log a of a. See, I don't want you to try to memorize that. I don't want you to read it. What this is saying is, I've got a base a. A to the power of what will give you a? Have a think about it. A to the power of what will give you a? Yeah, a to the power of 1 is just a, right? So that means log a of a must be 1. But that's one of the properties that you have to memorize apparently. But you don't need to. If you read what it actually is, logarithms is to solve for the power. Yeah, so for example, if I said 3 to the power of what gives you 9, all of you know that's 2. But if I asked you to write it as a log version, so log is to find the power. This one back then was exponentials was not finding the power. Exponential was to find the value. So 3 to the power of 2 you would say is 9. Here, we want x to be 2. So if you were to write that as a log, it's like 3 to the power of what gives you 9. That's what this means. 3 to the power of what gives you 9. So log 3 of 9, if you type that on a calculator, it should give you 2. Okay, so try to read it rather than memorize a bunch of formulas, because that's what makes logarithms feel much more difficult. So maybe write a sentence or something to help you understand it. But let's do a bit of practice for equivalence. Here we go. Let's scroll down. Example 1. Yeah, I want you to read this one. Can you see, when I say write an equivalent exponent statement for this exponent, what does log 2 of 16 mean? And I know the answer is 4 here because I wrote the 4 for you. But if you read it, what is this log 2, so log base 2 of 16 mean? What am I asking? Because you're trying to write an equivalent statement now. What's this as an exponential, Christina? Yeah, because this is real. Log is to tell you the power. So I know the power is 4. I know the base is 2. What they're saying is 2 to the power of what? In this case, it's 4. Will give you 16. That's what this is saying. When you read the logs, it's 2 to the power of what? Gives you that value. That's what log is doing. Log is trying to find the power. Let's try the next one. Oh, I already got that one. I just did that one with you before. A to the power of 1 equals A. Now, if what I just did still doesn't make sense, like you can't read it, here's the algebraic approach to it. Log 2 of 16 equals 4, right? If you want to do the get rid of log, what's the inverse of log? What's the inverse of log? It's like inverse of times is divide, then inverse of divide is times, right? So what's the inverse of log? Yeah, it's the power. But what base? So it's the exponent. And what's the base? What's the base for this one? Because he said inverse of log is exponential. So I'm like, great. So it's exponential. But what is the base? Artie? He said 2. Well done. Yes. Be more confident on it. Yes, it is 2. So if you want to undo this, if the problem is this log base 2, then do exponential. See, you can actually do it this way. You can say 2 to the power of log 2, 16. Whatever you do on the left, you do to the right. So I do 2 to the power of the right. See what I'm doing? I'm just doing literally the opposite of log, which you told me before was exponential. So 2 to the power of whatever's on the left, and 2 to the power of whatever's on the right. 2 to the power of 4, to the power of log 2 and 16. But we know these are inverses, so they're going to cancel out. So 2 to the power of log 2, 16, it's going to cancel out, and you end up with exactly the same equation that we just wrote over here. See what I'm saying? So it's just getting that familiarity. That's what makes it tricky for a lot of students, is to understand log is the opposite of exponential, and exponential is the opposite of log. That's it. It's exactly the way I just did over here. 3 to the power of log 3, they're inverses. They cancel out. Yeah? All right. Now that you've got that concept, you can fill out the next 2, C and D. That's for you. But let's evaluate. Shh. Example 2. Someone tell me what the answer is. I want you to read it, or you can do it algebraically, but I want you to tell me, what is log 7 of 49 equal to? 2. That is correct. This is the same thing as saying 7 to the power of what equals 49. Or you could have done it by saying 7 to the power of the left. And then that equals to 7 to the power of x. Okay, so these two cancel out. 7 to the power of what gives you 49? And we know it is 2. That's another way of doing it. All right, what about B? Log 3 of 1/9. Bit trickier. Who wants to have a go? Oh, Nimafi again. -2, not bad. This is the same thing as saying 3 to the power of what gives you 1/9. And you already had practiced this in the previous example or exercise. That's the same thing as writing 1/3 squared, which is the same thing as writing 3 to the -2. Therefore, x equals -2. Well done. So it does equal to -2. All right, flip over the next page. Here are some laws for you that you're going to use. Most students will remember 1 and 2. 3 is always examinable at year 12. And the rest I expect you to know just from logic. If you understand what logs was and what I just described, you don't need to memorize 4, 5, A and B. Okay, you just need the first 3 and you should be able to do the rest. So let's do the first one. Log law number 1. If you add 2 logs together and they have the same base, then you will multiply them. Okay, so it becomes x times y. It's kind of like the reverse of your index laws. So your index laws was if you times the indices and they have the same bases, you add the powers. In logs, it's the other way around. If you add the logs, then when you simplify, it becomes x times the y. Yeah? Similarly, again, with index laws, remember if you divide them, you subtract. Well, in this case, it's now subtract. Means you divide. So here this would be log base A of x over y. Third one is an examinable one. They always do it in exams. The rule says that you can bring the power to the front and it becomes n times log base A of x. Okay, it's going to be one of the key rules that you'll be using. And then the rest is an expansion of it. Okay, so everything else is an expansion. Log law number 4, essentially you can rewrite this as log A of x to the power of -1. And then use rule number 3, you can bring -1 down. So you get -1 times log A of x. Okay, can you see that? So 1 on x becomes x -1, but rule number 3, you can bring -1 to the front. That's why it's negative of log AX. All right, log 5A and 5B. Hopefully at this point, you should be able to tell me the answers for those rules. We already know log A of A is 1, because we're saying A to the power of what gives me A. Then what would this one be? What's log A of 1? 0. Very good. Because that's just saying A to the power of what gives you 1, A to the power of 0 gives you 1. That's index law number 6. But there you go. Those are your log rules. If you're wondering why is it when you add, it ends up being times, why it's the inverse of your exponential, you can actually prove it. Here we go. Let's say we've got these two. A to the power of m equals x. And we've got a to the power of n equals y. Right? Same bases, different powers. That means different results. That's why you get an x and you get a y, right? But if I asked you to write an equivalent logarithm, this is an equivalent logarithm. Base is a, so a to the power of what will give you x. You see that? I'm just saying. A to the power of what will give you x. What would the next equivalent expression be? How can I write a to the power of n equals y as a logarithm? Have a go with this one. What would this be? Beautiful. Okay, so I'm saying a to the power of n should equal to y. So a to the power of what will give you y? Now let's multiply them together. We know that in index laws, if you have the same bases and you multiply them together, you would add. You would add the power, so it's a to the power of m plus n, right? What's interesting is that when you say a to the m times a to the n, a to the m is equal to x, and a to the m is equal to y. So in a way, you're almost saying something like this. X times y. True? And that is equal to a to the power m plus n. So far, so good? Yeah? So all I did was I just literally used index laws here and said a to the power of m times a to the power of n equals a to the power of m plus n. Right? But a to the power of m was equal to x, and a to the power of n was equal to y, so it's really like saying x times y. Now from here, isn't this another exponential that you can rewrite as a logarithm? A to the power of something equals xy. So if you do what I just showed you just now, what's the equivalent log expression? So you can see it again. So if I write out the answer, log base a, so a to the power of what? So m plus n is over here, is equal to x times y. Can you see what I'm doing? This is the result. A to the power of what gives you that? Just like you did over here. A to the power of what gives you that? So a, that's log base a, to the power of what, that's my power, is equal to x times y. Okay, this step here was key. So that's the conversion. So if you understood this part of the conversion, try to see it in this way as well. Yeah? Once you can see that, well now you're pretty much at the home stretch. M is here, N is here. So if you replace M and N, this is how you get rule number 1. Rule number 1 comes from log A of x plus log A of n, y, is equal to log A of x times y. That's the only reason why the index laws came into play. Because when you added them, when you times them, you were adding the powers, but it's this bit. It's that conversion. When you convert exponentials to logs, it's the way you read it. You're saying log base a. When you say log base a of xy equals n plus n, you're really saying a to the power of n plus n equals xy. Just like you did over here, a to the power of n equals y. I'm just doing exactly the same things. That's how you get rule number 1. And if you do the same for division, index law number 2, you can get law number 2. And then if you then did rule number 3, same idea. That's how you get the index laws, okay, or the log laws. All right. Let's do 2 more examples. 2 more examples, and then I'll leave you guys to it because there's quite a bit of notes there, and I'll get you guys to practice a bit. Okay, so log rules. Yep. Sure. Here we go. First rule. Simplify this expression. Log A of 3 plus log A of 8. Which rule should I be using? We've got 5 of them. 1. Very good. Same bases. So they're both A's. If you add them together, you times the the numbers together. So in this case, it would be log A of 3 times 8, according to rule number 1. So then it's simplified to log A of 24. Well done. B. Which rule should I be using? Which one's B? Rule number? How do you simplify this one? B. 3, very good. 3, you can bring the power back up. So then becomes 4 squared. That is the same thing as saying log A of 16. Now, Rule number 3 is always likely the tricky one. When you do the exams, the number in front of log is the one I want you to pay attention to. This is a common mistake. Have a look at example 4. You know what the common mistake is for examiners? In exam 1, question 3, this is worth maybe 2 marks, sometimes 1. Most students will do this. What's the problem? Why can't they just use rule number 1 here? Because we said same bases times the inside. They have the same bases. I got 16 and 5. Why can't I do 16 times 5? Which is there, and that's log base 10. What's the problem? Log 10 to the 5. That's good. Good. You actually have to bring the 2 up to the 5, and you have to bring the half to the 16 before you even combine these two. The reason why is because rule number 1 never said you can have a value at the front. It never said that. If you look at the rules number 1 and 2, never had an A value at the front. There's nothing timesing it. So already from the get-go, you could not use rule number 1 and just ignore the half of the 2 and just work in the inside. You can't do that. But most people will see the plus, see the bases, and then combine it straight away. You have to get rid of that half and 2 first. Okay, so this is the wrong approach. How do you actually do it? Well, you have to use rule number 3 first. Rule number 3, so rule 3 now becomes log 10, 16 to the power of half, plus log 10, 5 squared. This is okay to use rule number 1 now. See, there's no numbers at the front. Rule number 1 never talked about it. So here, this is when you then say it's log 10 of 16 to the power of half times 5 squared. Now let's see how your index laws are. What's 16 to the power of half the same as? Anyone remember? What's to the power of half mean? Square root. Very good. So square root of 16, that's 4. 4 times 25. What's 4 times 25? Four times 25, team. 100. Then, don't stop here. You won't get your marks if you stop here. You actually have to evaluate that. What's log 10 of 100? 2, good, because this actually means 10 to the power of what? Gives you 100. So the answer is 2. If you left your answer here, examiners will assume you don't understand logs, and they will penalize you there. So log 10 of 100 is not good. This is good. Okay, you must write the 2. All right, team, I'll stop there. You've got 5 laws. You've learned how to read logarithmic expressions. That's probably the hardest part conceptually. The rest is about practicing your algebra, but you need the algebra to solve for logarithms. That means then you can sketch. Okay, and hence you can go back to exponentials and solve that. That's the next exercise. But for now, just stop there. We'll continue on with our next lesson on Wednesday, and I'll just readapt this bit and add a bit more. Okay, I'm going to pause there. So this is your time now.